This is called separation of variables, and this is a standard trick used in classical mechanics. This is called the Hamiltonian. Hi, so welcome back, everyone. Um, for those who are joining me for the first time, hi, my name is Ognivo, and this is my YouTube channel. Together, we study quantum mechanics. Specifically, if we follow this book by Griffiths, and yeah, this is typically aimed for undergraduates and advanced high school students. So if you're either an undergraduate and or high school student soon going to attend college, maybe this course or this discussions in quantum mechanics might be helpful for you. Okay, so let's begin again. So previously we had 4 lectures, lecture 1 to 4, where we talked about the wave function and the probability interpretation of the wave function, as well as we talked about some probability measures like the standard deviation and the mean. And we had a tutorial session based on them, which was in the video tutorial 1. All of these are in my playlist, so if you guys are interested and if you want to go through them again, they will be in the playlist. So let's begin. So today would be lecture 5, and finally we would talk about solving the actual wave function. So recall that I had mentioned that if you somehow if you can solve for this wave function psi of xt, recall that this is a function of both x and t being time, x being position. If you can find this guy out by solving the Schrodinger equation, which was introduced, by the way, in lecture 1, Schrodinger equation, then you can find the expectation value of any operator. Simply from this integral, minus infinity to infinity dx fx t mod psi square. And you need a mod here because, as I had explained, this is typically a complex number. This is typically a complex function, actually. So a good question right now would be to ask, how is it that I actually solve for a psi x of t? So the point is to solve this equation, which we have seen a few times now. Plus the potential term. So this is the Schrodinger equation again, and somehow if you can solve this equation for given potential term, then you are done if you can solve for psi x of t. But as is life often, this is generally a hard problem, generally difficult to solve for arbitrary v x. And the whole point of this course would be to solve this equation for relatively simpler potentials Vx up to the hydrogen atom. And you'll see that even within quotes relatively simple potentials, you can solve some very complicated systems, like for example your hydrogen atom, or any atom for that matter. Okay, good. So what would the strategy be to solve this equation? Well, for those who the strategy is to try and have an ansatz. This is called an ansatz. Ansatz means a guess. So we will try and guess a particular form of a solution. So what is the guess that we can have? What is a well motivated guess? Well, the well motivated guess is called the separation of variables, and we will try and imagine that this is our ansatz, or in other words, the wave function factorizes in this particular form. Recall that this method that we are discussing is called the separation of variables. This is called separation of variables, and this is a standard trick you would use for solving a lot of differential equations down the line. As you study more maths and more physics, you will see that this is the first line of attack that you can have for solving these problems analytically. And it's called separation of variables for obvious reasons, because you're separating these functional dependencies. Note that this is actually not true for general functions, right? This should make you uncomfortable. It is not true, for example, that any f of x and t can be written as, say, f1 of x times f2, some other function. F1 and f2 are other different functions, not necessarily the same. This is not true. A classic example, or a very simple example, I would say, is take any function, right? Say x squared, your f of x comma t is x squared t plus, say, 5t squared plus 6x, whatever, right? In fact, most functions are not of this form. So you see, this is not in the form of a particular f of x times some other function of t, right? However, that's why it's called an ansatz. That's why it's called a guess. Let's guess that the wave function that we are trying to solve is indeed of this form. Okay, if that be the case, then what happens? Why is this method, this named method, of course, as you can see, this method has a name, so it must be quite a famous and quite a useful method. So let's check out why is it that this method is useful. Well, if now you go back to your Schrodinger equation, which is here, copy, paste, and substitute this ansatz that you had a magic happens. What's that? You can immediately see that you will get an sorry, there is no minus here. There's a typo. There's no minus here. Yeah. IH cut psi times del f del t is equal to minus x square del psi del x square times f plus v psi f again. I need to be a bit careful. This is small psi notation. Maybe I'll specify it here. Capital psi is a function of x and t, but small psi is just a function of x, right? This was your ansatz that you had chosen here. Small psi is just a function of x, and capital psi is the wave function. Actual wave function is, of course, a function of both x and t. Okay. And then if you divide by, firstly, it's obvious that you'll get this equation, right? Because in the actual Schrodinger equation, only the f carries the t dependence and psi has nothing to do with t, and vice versa. F has nothing to do with x and psi carries the x dependence. So once you make these operators act on the wave function, and that's why the method of separation of variables is so useful. It actually decouples in this manner. Or in other words, if I divide by psi times f, you will see why the magic happens. You get a f of del f by d. I am dividing this entire equation by psi times f, small psi times f. One by psi times minus h squared by t 2 psi tx squared plus v, right? So in going from here to here, I'm dividing by psi, small psi, times f. You get this, right? And you see, this is why this is so useful. This left-hand side is just a function of function of time. And this right-hand side is a function of x. And that can only happen. So the structure, for example, is some capital F of x is equal to some capital G of t, right? This is the structure. And immediately you know that this can happen only if either side is actually constant, right? So this has to be some constant, and this has to be some constant. Otherwise, this equation cannot hold. And that's the beauty of the separation of variables. That individually, each of these left-hand side and right-hand side have to be constants. Great. So that's the beauty of it. So immediately, you can solve at least one of them. So you have, let's call it, it's conventional to call it IH cross 1 by f df dt. The separation of variable constant to be e. You'll see why it's called e. And for those who are following, this e is for energy of your system. This equation is just this equation, as well as this equation also has to be E. So that's the whole game. This equation is very, very easy to solve, right? Can you solve it? If you guys are following, can you solve it? Or can you write this expression before I do? Well, this expression would simply be e to the power minus I by h cut e times t. Right? Why? Because if you derivate it with respect to t and divide by f, then it's easy to see that this equation holds. Basically, these kind of equations will generate phases for you. By phase, I mean exponential of some I times some real number or real function. Great. So you have already solved for half of the problem. What happens to the other half? Well, let's see what happens to the other half. So you are left with this part of the equation, right? Let's copy because I'm lazy. And as I have explained, that this has to also be equal to the same constant, right? The same constant. That is, this is equal to E, and this is also equal to E. That's the only way this equation can be satisfied. And that's the beauty of the separation of variables. Okay, great. So now we are done, and this equation reduces to a very, very famous equation. Probably the most famous equation in this course. And this equation is called the time-independent Schrodinger equation, which is the most famous equation that you would be solving in this course. And for given V, the entire program would be to solve this equation and find out what this small psi is, which is the time-independent wave function. Okay? Okay, great. So this is time-independent Schrodinger equation. Why time independent? Well, because you see from this expression, everything is just a function of x, right? So everything is just a function of x. There is no time dependence anymore. Of course, the original problem had a time dependence, but using the clever ansatz and this separation of phase method, you have solved for the time dependence part, and this is the time dependence part. So your actual wave function, which was psi, a function of both x and t, as I've mentioned, is psi x times e to the power minus I by h cross E times t. And this is the small psi that would be solving from this equation. Once you solve for small psi here, you plug it back here in this equation, and you have figured out then your actual quantum mechanical wave function, right? That's sort of where we are gonna head for the next quite a few lectures. Okay, great. So what I also wanted to highlight is why do I care about these solutions? Well, for one, this actually, as you saw, this helps you solve the problem, right? This helps you solve this complicated differential equation. And unless you assume this ansatz, there is no way you can separate the variables, and there is no way you can reduce your partial differential equation to ordinary differential equations. Recall, I have been careful to write these as ordinary differential equation. You see that this is ddx, for example, and not del x. So it's not a partial differential equation. But other than that, why is it that I care about these solutions? Well, let's see what these solutions physically mean. For that, I need to introduce a notation. So you see in the time-independent Schrodinger equation, which I have written here, let me call this H, which is, beg your pardon, this should be H. Basically, what did I call H? It's simply this part, the operator acting on psi here. Is it easy to see? So if I define, this is definition. I've not done anything particularly intelligent. I've just defined it. If this is what I define as H, then you see the above the in time independent equation becomes H psi is equal to E psi. Can you see that? Let's look at this equation, for example. This equation is the same as this equation, this tiny little simple looking expression, provided you define this H in this particular manner. This H that I had just defined here is called the Hamiltonian. In classical mechanics, this is called the Hamiltonian. And for those of you who would take up physics later or are undergoing physics courses, this is the object of concern in classical field theory, right? It's called the Hamiltonian. In high school physics, you had known them as energy. This Hamiltonian is the energy gives you the energy of the system. And you see that even in quantum mechanics that holds, right? Because this Hamiltonian acting on the wave function gives you, as I had mentioned, this E is the energy, so it gives you the energy of the system, right? In field theory, this operator is called the Hamiltonian. So remember this name. We'll use it ever so often. If you go back to lecture 2 and 3, by the way, recall that we had found the momentum operator, which was minus I, sorry. Minus I H cross by del x. This was in lecture 2 or 3, lecture 2 and 3. So with this notation, you can write this h simply as p square by 2m plus v. Does this look familiar to you? In special relativity, p square by 2m plus v, rather this p square by 2m is in classical mechanics half mv square, right? Why? Because p is mv in classical mechanics, in the physics that you know. So you see, even in quantum mechanics, this expression reduces to the known expressions, right? So p square by 2m is your half mv square, v is the potential energy, so this is kinetic energy plus potential energy, which is given by the Hamiltonian. And that's why, as we had discussed in lecture 2 and 3, this is called the momentum operator in quantum mechanics. Great, we are doing really well. So the one thing I wanted to check is this: in these stationary states, these states that we had found, these states that we had found are called stationary states. Why is that? Well, you can immediately check something. Imagine you have, for example, H acting on psi, we had seen equal to E psi. This is this equation. Imagine I want to find the average expectation value of H and a standard deviation of H. Or in other words, I want to measure H, and if I measure it multiple times, I want to see how the value of H that I get is distributed. That's what the standard deviation does, right? It tells you how distributed your outcomes are. We have seen that, right? We had drawn a Gaussian like this, and I had told you that this sigma measures how wide this is. So this the bigger the sigma, the wider it is. For example, if you have something like this has much less distribution, this is much less standard deviation. So I want to measure on this system, on this stationary states that I had found out here in this green highlighted state. I want to find out how the Hamiltonian, what the eigenvalues of the Hamiltonian is. As an aside, let me tell you that this is called an eigenvalue equation. Why? Because you have an H, which is an operator here, the operator being given by this expression that I wrote, so differential operator, and the right hand side is just a constant number. Recall, this E is a constant, it's not a function of X, right? You recall that, right? That this is a constant. So it's something like a 5 or a 7 or a 2 or whatever. So this equation, the type of equation, is an operator acting on some function, say, gives you a number times that function. This is called an eigenvalue equation. and E is called the eigenvalue of the operator H. Well, H in this particular case. Great. So let's figure out H. We have seen multiple times that this is given by psi Tx, capital psi, always H, capital psi, star. But you see, that's again the beauty of it, because the phase factor, this we have discussed at some point, is minus I by H cross some ET. This is the phase of psi. So the phase of psi star would be by H cross the opposite, the inverse, right? This would be that of the psi star, which means this equation, this term actually doesn't arise, right? Because they cancel from here and here. So this is the same as time independent Schrodinger equation. These psi's are the time independent. But I know that this is actually E psi from this equation, from this equation here. So this gives me E times dx mod psi square. But this equation is normalized to 1. So this gives me E. Likewise, exactly similarly, that's the power of these differential eigenvalue equations. For example, now if you have an H here again, or in other words, if you are to evaluate H square psi, you would get exactly E square. Why is that? Because you see, H acting on H of psi is H E of psi, but E is just a number. So right? So you would have the same thing, dx mod psi square is equal to E square. And then we already know the standard deviation on these states is given by, you know this, right? So tell me, it's expectation value of the square minus the square of the expectation value. The standard deviation is given by the square root of it. But this is E square, this is E square, so this is actually 0. So this tells you that in stationary states, are eigenstates of the Hamiltonian, and they have fixed energy. E here in this particular case. Okay, so yeah, that is great. Now I want to mention a slight higher point, that the general solution of your Schrodinger equation, this psi x of t, would be a superimposition of these psi n power minus I by h cross en of t. So this is the most general solution of your Schrodinger equation, where individually each size satisfy the time independent Schrodinger equation, with En being the energy corresponding to psi n, exactly as we had the separation constant E for this particular problem, just as we had the separation constant E for this psi. So the goal would be to solve for all such psi's, multiple psi's corresponding to multiple ENs, and take this linear superposition. And this would be the general solution of your Schrodinger equation. Okay, good. So that's where we can stop today. And yeah, so see you next class. Yeah.